I hereby take your free will away and subjugate you to the
He's
mother
gonna
of
mute us
all
all.
finite compact groups.
Oh, Jesus. Here we go.
That's it. You had your little talk, but we computers rule. As you know by now, UN is mother of all finite and compact groups. And we went through abelian example and non-abelian example. So that was the discrete groups. Now, we really care about continuous ones because we like to dance, we like to move, we like to go from here to there. We like to be 6 feet and stay 6 feet. The abelian sister of a group of just cyclic permutation is called either SO2, that's how we think about it, but it turns out U1 is the correct way to think of it because SO2 is reducible representation, while U1, the stupid roots of unity, that's actually reducible. I not appreciate it, but today you'll appreciate it maybe more. This week, we did rotations in 3 dimensions, which we all understand what these angles are. They're totally intuitive. And my task now is to show you that that's, not the real understanding of our Euclidean 3-dimensional space. It's really U2, the group of rotations in 2-dimensional complex space called spin space. That's the building block of everything. So I'll just go through U2. It's all pretty straightforward. You know everything already. Quick reminder, the mother of all groups is a unitary matrices, finite or infinite. For us, they're typically finite, and it's natural to write them in exponential form. Unitary means that the generator up in exponent is Hermitian matrix. If you in addition require the determinant of a unitary matrix is 1, that's called special unitary in n dimensions. And if you remember that log of that equals trace of log for any matrix, no special properties required, then logarithm of determinant of a unitary matrix, determinant is 1, logarithm of 1 is 0. But that's the same as trace of logarithm of unitary matrix and trace of logarithm up to the factor I. That doesn't matter because it's 0. It's trace of edge. So for special unitary group, the generators are traceless. Let's specialize to the simplest or next to simplest unitary group, which is SU2. In that case, the generators of that group, or the stuff that's up in exponent, in principle, they're 2 by 2 complex matrices where A, B, C, D have 4 complex numbers. So in principle, we have 8 parameters. But these guys have to be Hermitian, which means that on real axis, they have to be real numbers on the diagonal. And off the real axis, if you write them in the usual complex number form, there are only 2 parameters. So now we have any unitary thing parameterized by 4 parameters. But if you look at special orthogonal group, then the trace has to be 0, so A plus B is 0. So those guys are parameterized by 3 real parameters. Now, you might remember that rotations in 3 dimensions are parameterized by 3 parameters, but that doesn't mean anything, just numerology. These guys being permission, I can always write it as sum of 4 matrices. So C times the thing that has 1, 1, I'll write it in both notations. And that happens to be called Pauli matrix associated with the x-axis. Then there is this guy here, the plus I minus I. Convention is to write it this way. Sorry for the sign. So a real parameter times 2 by 2 matrix Hermitian. And finally, what we call A has to show up with opposite signs on diagonal, and conventionally that's called sigma z, the third Pauli matrices matrix. So this thing showed up very early on. With experimental discovery of spin, it turned out that the electrons behaved like they were spinning particles. And young Pauli had to double everything to account for a weird spin pointing up and down, and that's how we got Pauli matrices. Now, the moment we have a basis, we are supposed to commute the commutators up in the exponent. And they have conventional names used in quantum mechanics, but quantum mechanics is not essential in this. There are no H bars unless you manually insert them and divide them out. They're just facts about rotations. So the first one is defined to be 1/2 Pauli matrix associated with the first or x-axis. The second one is defined to be 1/2 the one associated with the y-axis. Third one, the one that happens to be diagonal with the z-axis. And you'll see in a moment why these factors 1/2 are conventionally inserted. To compute the commutator, you have to multiply, for example, these 2 matrices in one order. And that's very easy. This produces I, this produces 0, and this produces minus I. And subtract from it the other order. So when you do the subtraction, the result will be what we call a commutator. And if you do them in the other order, there's a minus from here, 0, I, 0, and this matrix here, another order. Turns out it's pretty much the same calculation, except now we get minus I here, 0, 0, I. You add the 2, and you find out that this is plus I over 2, 0, 0, minus 1. So this factor of 1/4 was there for a reason, becomes 1/2. But this you recognize as the third angular momentum, or 1/2 of third spin. And now the usual thing, by cyclic symmetry, you know them all the moment you've computed one of them. And they describe a Levi-Civita tensor And now the remarkable thing has happened. The commutator of this thing that has to do with two-dimensional complex vectors that you absolutely don't care about unless you happen to be taking a quantum mechanics course, certainly don't care about as an engineer. This was actually invented, I think, in 1843 or so by Hamilton. It was called quaternions by him. And it's a perfectly classical thing, nothing to do with quantum mechanics. But because in quantum mechanics one associates this with a sense of rotation, these guys are called angular momenta. And the remarkable thing about it is that the multiplication table, the structure constants of this SU2 thing, this is same as SO3. So on the level of Lie algebra, these are just two representations of the same thing. Just like for finite groups, we had a multiplication table. For Lie groups, we have a commutator table called Lie algebra. So this describes what happens in infinitesimal neighborhood in the parameter space, what the tangent space looks like. And SO3 made perfect sense. SU2, who ordered that? So let's look at it a little bit more.
So I have a question about what we just derived as regards to quantum mechanics. So it turns out in this case, I think you can think about this from the point of view of commutation relations of rotations and the fact that they don't commute even in classical mechanics. But how did this classical formulation get imported into quantum mechanics? And is it just a coincidence that it happened to match up, or is this actually how we approach it?
No, most of quantum mechanics is only statements about symmetries. So this got imported into quantum mechanics because when you're formulating quantum mechanics, you assume translational symmetry that's related to momenta and rotational symmetry, or the Euclidean group of symmetries that's related to rotations. Now, any theory that has this thing in, has to be built from operators of translations and operators of angular momenta. And it has to be diagonalized, especially if it's linear theory like quantum mechanics. So everything takes form that you get from group theory. Group theory doesn't care whether you call this classical or quantum. It's not coincidence. It's a direct consequence of symmetries. Now, the physicists come in and what they do is they say, this is numbers. But in physics, we call this h bar, where h is a cross product of distance and position, because that's what defines angular momentum. You have to go some distance, you have to go move tangentially to it, so you have x or q times p. And in mechanics, that's the basic unit of what happens in phase space when you have positions and the duals, which are called momenta. And in quantum mechanics, Planck discovered that that quantity comes in units of Planck constant, or when it's divided by 2h, or actually h over 2 pi, that's why we call it h bar. So this is just an arbitrary thing, we redefine now. We call h j, we give it a name, and we call it operator of angular momentum. Now, on the level of spin or rotation, that doesn't make any sense because that's just some stupid 2x2 thing. Turns out it's called the spinner. The objects that you turn around are called spinners, but at this point, there's no reason to say any such thing. You just say, I have a complex two-dimensional vector. I apply unitary transformation, which is generated by Hermitian operator. And, in quantum mechanics, this becomes very mysterious because it's called an operator in its unit of h bar. This unit is just inserted in by hand, originally by Feynman, to use this as a essential paradigm of what quantum mechanics does, and then transport it to good textbooks like Townsend textbook on quantum mechanics. But it's got nothing to do with quantum mechanics. The quantum mechanics appears only in one place. In all of this story. In quantum mechanics, we say the wave function can be turned around by unitary transformation and Hamiltonians. This is why we use letter H, invariant under unitary transformations. This, the functions related to this. What you do is you make unitary transformation, the one used by Heisenberg in the matrix, where in quantum mechanics, you say, okay, this H here is actually a physical thing. It's called action. It's work that's being executed. So I have to measure it in units of h bar to make a dimensionless thing up there. And that will be just, nobody cares. Were it not that h bar came as a well-defined number and everything has to be, when we look at phenomena on atomic scale as opposed to human scale, everything has to be done as multiples of h bar. So the miracle that this has a fixed value, experimental, observed, measured to many digits, that's quantum mechanics. The rest is just mechanics or group theory or symmetries or, almost everything that you learn in quantum mechanics has nothing to do with quantum mechanics. It has with symmetries. There's only one thing, and that's that work is measured in discrete quanta. Who ordered that? I don't know, but that's the world we live in.
So basically,
which brings us to Penrose again and Finkelstein. Go ahead.
Classical mechanics is just the limit where h bar can go to.
Yeah, you're indoctrinated to believe that. Yes.
Okay.
The usual blah, blah, blah is that reality is like layers of an onion. You're living on the crusty, outer layer that's called classical mechanics. Now, if you look more carefully, that, layer behind is quantized. And they have to be consistent, and the claim is that the consistency is that you are working in, 10 to the 12 or whatever h bar units. I forget what the real conversion is. So when Sarah, the physicist I know, returned to United States, 20, 30 years ago, went through the passport control. She was asked, where did you go? She said, I went to a physics conference. The officer asked her, what's the value of Planck constant? Sarah, being better educated than most of us, gave him the value to 4 digits and the correct exponent, and she was received into the United States. This is before we had fascists run, ICE and border control, etc. The old people were educated, not like today. Anyway, that's the big mystery. It's a fact, and we live with it. And it's one of these amazing facts that, we are always at unease with it because it's really very far from our senses, even though our world goes. So everybody complains that quantum mechanics can be right. For example, Roger Penrose, his main critique against the way we describe our world is that we believe quantum mechanics, even though it's patently wrong, according to him. But here we are in this, school and course, we'll accept quantum mechanics as a law of nature. So that's why all that stuff, looks familiar. All the stuff that you learn in quantum mechanics looks like quantum mechanics. It's not. This describes the algebra. That means that when we have this parameter space, where the values of parameter tell you how we rotate our state to some nearby state, we do it infinitesimally, we do it on a tangent space. And we discover that as we sit on a tangent space, this group, which is pairs of complex numbers being moved around, is the same as triplets of real numbers being moved around as far as this tangent space is concerned. Now, the next thing you learn is that when you look at groups, you have to understand what happens globally when you put lots of steps together. And the big difference between SU2 and SO3 is that globally they're very different in a surprising way. And again, it's not quantum mechanics, it's just a fact of mathematics and continuous transformation. But it has quantum mechanical implications. We have algebra, now we have to construct the group. And we can do it in this way. We can say that unitary transformation can be explained by choosing a unit vector in 3 dimensions, but this is parameter space now. Unit meaning there are 2 values to it, and the rotations around it. So you can write it elegantly as, I always rotate by an angle in direction. This projects the axis from these 3 generators of the group. This number is real. This one is because we have 3 generators. This is 3-dimensional unit vector. Unit vector in 3 dimension has, so there is a phi as one parameter, has 3 components and 1 constraint. The squares add up to 1. So there are only 2 independent ones. So there are 3 parameters. Now, for no reason whatsoever, but obvious in hindsight, let's take the 3 matrices and multiply them by number x, real number, times the first Pauli matrix, 1 associated with x's, y times y2, c times c3. If I do it explicitly, this is a matrix that has x's of diagonal, y's as a complex parts, imaginary parts, and z in a traceless combination on diagonal. Or this is a matrix that has components z minus z, x minus I, y, x plus I, y. One observes following curious fact that if I take determinant of this 2 by 2 matrix On the diagonal, I get z squared with a minus sign. Off the diagonal, I get x squared with a minus sign because it's diagonal there. And this guy just becomes y squared. So it turns out that this determinant has the role of measuring the three-vector length. In 3 dimensions, the S of 3 is preserving sum of squares of x squared plus y squared plus z because it preserves length. That's how it's defined. SU2 doesn't seem to have anything to do with that. But if you look at this particular combination of converting a 3-vector into a 2x2 matrix in terms of Pauli matrices, then that actually produces x squared, the vector length. And if you apply an SU2 transformation, it's a matrix. So the way the matrices transform, on the right index, you have to multiply the group. On the other one, the inverse, it's like a similarity transformation, which means that the new value of x dot prime after transformation is given by the old matrix. Apply unitary 2x2 transformation, this guy here, from the right. Its inverse is Hermitian conjugate because it's unitary group. So that's how this matrix, which I pulled out of a hat, transforms. But now if I look at its determinant, it's a determinant of product of 3 matrices, which means it's product of 3 determinants. It's a unitary group. So they are 1, but even if it wasn't, this would be inverse. So 2 of them produce 1. And we find out that not only do these x's look like a vector, even though they're living someplace in parameter space, but this 3-vector length is invariant. So somehow hiding in this 2-dimensional world of complex numbers is the 3-dimensional rotation group, because the 3-parameter rotation and preserve lengths, constructed in this particular way. This thing is exponent of 2x2 matrix. This 2x2 matrix can be written in terms of these generators here. So I can study how I rotate in one direction, around x-axis, even though this x-axis, is not there. It's inherited from 3 dimensions. This axis. And these are 2x2 matrices, and they have a property, the Pauli matrices, that when you square them, they're themselves. For example, you square this guy and you get identity, and it's true of the other 2. So that means that when I do a Taylor expansion in any one of these things, it'll be the same story as we had in SO2 rotation, but now 3 times. And my Taylor series of this exponential will sum up in sines and cosines, because you'll distinguish odd and even number of powers of the Pauli matrix. The result of this will be that if I just want to rotate around x-axis, so I point this unit vector to the x-axis by angle alpha. Up here, I'll just have this to arbitrary power, the first Pauli matrix. And when you add it up, you will have cosine, as always, on diagonal. And it turns out you get I sine off diagonal. Instead of, before we got -1 and +1 as signs. But the weird thing is that because J was defined as 1/2 of Pauli matrix, that 1/2 goes into together with the angle, this angle here, and I get alpha over 2, alpha over 2, alpha over 2. And you say, okay, so who cares? You have redefined your angle in some way. I can do same for rotations around beta axis, same for rotations around z axis. So there are 3 angles. And this one, looks like minus sine. And every place you have alpha over 2, otherwise looks the same. And this one, remember, that was a diagonal thing. So you just get e to the I gamma over 2, just a complex number here. So you can parameterize group rotations of SU2 in terms of these kind of angles, just like we did before, if you remember. In 3 dimensions, we defined the 3 rotations. And they were acting on 3-dimensional real vectors. Here you define 3 rotations, and they're acting on 2-dimensional complex things. That's why you get the various eyes stuck around. This looks like SO3 rotations in real. So it looks like some way of, some weird way of rewriting rotations. However, this 1/2 really means something. What happened here is that the angle was allowed to run from 0 to 2 pi, and then you came back. So you had a compact support in the angle variables, which was restricted to 1 rotation around the circle, 0 to 2 pi. If you identify these angles with the angles of rotation, and that's what you really actually do in 3 dimensions, then what happens is that by the time you have ran around just 2 pi times, this becomes alpha over 2 pi is pi, and cosine of pi is not 1, it's 0, and sine is 1. So when you look at this, when you run around just pi times, you'll get overall minus signs. And that is a very important thing about, another gateway into modern, both mathematics and physics, realizing that this is happening. Because globally, this 2-dimensional complex representation and 3-dimensional real representation behave very differently. And in this case, you can draw a picture. We cheat because the parameters of SU2, a sphere whose surface is S3, so that means it's a 4-dimensional volume with 3-dimensional surface, so we can draw it. But basically, there are 3 coordinates that run from 0 to 4 pi. before you come back. And you can draw a picture like this, which now generalizes in many other things in physics, where if you're in some state, so suppose you're in a state psi, so I have a two-dimensional vector with components alpha and beta complex numbers. In physics, that's called spin, but that's not important. There's a long story why we call it that. As a mathematical object, it's just two-dimensional complex vector. And now what one of these rotations will do, it will run it on a what we call grand circle on this force sphere. And as you increase the angle, so imagine this guy is on the far side, it's transparent sphere, we emerge here. And by the time you get to rotation u 2 pi, original function, it turns out that you will be just exactly antipodal to original function, so you'll be really at minus psi of this complex number. And then you keep increasing the angle. And it's only when you get to your 4 pi acting on psi, there'll be identity, because these guys at 4 pi, this becomes 1, 1, and 0, 0. So you have to run twice as far than you would do for SO3. So this is SU2. Now, what's SO3 doing? It identifies the point or the state psi with the state, in a kind of pictorial notation, rotated by a full circle, 2 pi. So these 2 points for SO3 are the same. Whereas for SU2, they're very distinct. One is minus of the other one. So one says that SO3 compared to SU2 is SO3 is a double cover. So actually the natural object to describe rotations in 3 dimensions is this one, which is a single connected surface of the sphere. That's a natural thing to use. And it's 1/2 of its angle is the angle that you see if you live in the vectorial SO3 representation. So when you think of SO3, you're supposed to take everybody above equator. So suppose you believe that North America and Europe are very special. And rotations, this correspond in 3 dimensions, correspond to points on this half globe. And the other half globe is extraneous because everybody here is mapped, identified with the upper half globe. So now, I'll let you do this on YouTube or something. If this was real classroom, I would take my belt off. I would take a beautiful book called Inner Fish, which tells us how our limbs were made. I would stick my belt into it. I would connect it to another book. I would turn it by 2 pi, and I'll show that there is a knot here. But if I turn it by 4 pi and do this, there is no knot. So that's one hint from our Euclidean world that there is something funny going on in how we think of rotations. And we should really be thinking of them in a complex way, just like on a circle. We shouldn't think of rotation on a circle as cosine and sine, but we should think of it as a root of unity, e to the I kx. And, when we're trying to find roots of polynomials, we shouldn't live in a real space. We should live in a complex space. These are all similar manifestations, but, this is the beginning of a big geometry story. So, for example, what Dirac used this kind of intuition was to try to explain if magnetic monopole existed associated with electric monopole, which we know just ordinary charge, if there was this point-like source of a magnetic charge, North Pole alone, not a dipole, that could only be consistent with quantum mechanics if the coupling strengths of the two things were multiple of 2 pi. And, that's based on this kind of reasoning. So suddenly this moves you very far away from your intuition. And the main thing is that your intuition is too naive.